Hi, morning guys. Today's lecture is going to be continuing on our spectrum analysis series, and we're going to be focusing on the short time Fourier transform, also known as the STFT. So far in all the lectures we have done, the analysis we did was basically on where signals where the frequency content did not vary with time, and these are referred to as stationary signals. But the question arises that how do we analyze the signal when the spectrum actually varies with time? And a good example of this would be music or real-time signals, which are non-stationary signals. And particular, stationarity is a tool used in the time series analysis where raw data is often transformed to become stationary. So like, for example, if you have a signal and you calculate the mean, variance, and other statistical parameters in it, it will remain constant over time for stationarity. So, in a signal like this, there isn't really a constant frequency or constant frequency content. Is basically the frequency content keeps on varying all over the place as the signal goes on with respect to time. Now, in order to analyze this, you actually need to use a slide-in time window. So the signal is typically broken up into frames or parts, and each frame is analyzed depending on the width of the window. And after each one frame is analyzed, the window slides accordingly to the next frame, and that analyzes and continues going on until all the frames are processed, and then it computes the entire FFT accordingly for it. While each frame is being processed, the FFT is computed for each frame, and accordingly, while it keeps on going, it kind of operates like somewhat similar to a running average. So it keeps on approximating the FFT until it actually gets like if it did the original FFT for the entire signal. So basically, we set the sliding time window with a fixed width, and we are, for each instance of where the sliding time window is for each frame, we apply the FFT to get the frequency content for that particular frame, and then we slide the window to the next part of the signal, to basically to the next frame, and we redo the FFT, and we keep on going until the entire signal is covered. And this process is referred to as the short time Fourier transform, or STFT, of the signal. So visually what happens here is that, let's say this grey box that we're observing is our slide-in time window, and let's say for here in particular, for the width of this is like our instance of a frame within the signal itself. So it's like one frame here, then 2 frames, 3 frames, 4 frames, and it keeps on going. So for each frame that the window occupies, it calculates the FFT, then it will slide accordingly to the next frame, and then calculate the FFT again, and then to the other frame, and keep on repeating until it reaches the end of the signal accordingly. So one thing to note in particular is that this window size, and I kept on saying it in my explanations, was that there's going to be a width for this window size, and this is referred to as capital NW. The shape of the window can be any one of those sampling windows that we saw in the previous lecture. So it could be a rectangular window, it could be a triangular window, it could be a Hammond window, it can be different shapes depending on like how we intend to sample the signal itself. And the spectrum is basically, when it now starts off, it's really a rough approximation, but as the window keeps on sliding and the FFT keeps on computing, it keeps on approximating and evens out like to the actual FFT of the entire signal. So in doing this, each result here will actually have time, frequency, and amplitude characteristics, and you can display each of them separately, but in most cases, when you're actually dealing with such things, you're going to get a special figure known as a spectrogram, where the x and y axis will be like time and frequency, where the amplitude itself is going to be shown in color. And one thing to note is that even though the spectrogram may be referred to as a plot, it actually is an image, not a plot. So to give you an idea what it looks like, this is actually an image of a spectrogram. And you can see here on the x-axis, this is the time axis, the y-axis here is frequency, and then the range of colors here given by this color map here represents the amplitude of the signal. So, to give you an idea of how spectrograms differ between two people who may speak, let's watch this in particular, where we have a spectrogram here where two different people are saying the word hello. And we can see here in particular that they do occur at the same time, which is like 1 second. They have different amplitudes, because we can see here that there's more red around here. But if we watch the frequency content, we can see here that there's more frequency here in between the 4000 to 6000 Hz range. And in this one in particular, the frequency content tends to be more from the 0 to 4000 Hz range, and it fades accordingly. So this is actually a good example of a real world application for when you're actually taking the spectrum of two different people talking. So for this spectrogram in particular, on the left hand side, this is actually the voice of a male person, because male people tend to have lower frequencies than female people. So this is actually the voice of a male person speaking hello. And we can observe this by the frequency content here, being that it's in between 0 to 4000 Hz. And this one here is a female person who's speaking, because the frequency content is more like 0 to 6000 Hz, showing that the frequency content is more on a higher frequency than a lower frequency here, because female people tend to have higher frequency voices. So in particular, when you're using sliding windows for the STFT, you want to use triangular, Hamming, anything else besides rectangular. And the reason why you don't want to use rectangular is that the rectangular window still contains side lobes which may be unwanted in the system. And we observed in the previous lecture that those side lobes tend to have some sort of magnitude associated with them. They're not fully mitigated. So those magnitudes that are associated with those side lobes, because of the rectangular window, they tend to interfere with the signal and the frequency content of the signal accordingly. So you really don't want to use a rectangular window when you're processing. You can use triangular, you could use Hamming, you could use Blackman-Harris, and so forth. So in the initial explanation, I said basically that you could have the window on one part, then you perform the FFT, then you could just go to the next part or the next frame and perform the FFT and so forth, right? But you also may want to actually think about overlapping the windows in particular. And in most cases, the overlap tends to be like 0.5 the width of the window. And the width actually is measured at the base of the window here. So it's not measured at the top, it's not measured at the center, it's actually measured at the base of the window. The overlap factor means that instead of these windows never intersecting, now you actually have the intersection of the windows occurring, and in this case it's actually 0.5 the width of the window. So in setting the window width, we also set the frequency resolution, and in that case, that means that the equation associated here, delta FW is equal to f of s divided by n of w, where n of w is going to be the width of our window. And nw is going to be less than n, where n is the number of samples for the entire signal. So in doing this, basically the frequency resolution gets decreased, yes, but associatively the time resolution is increased. Now if you wish to actually observe the spectrogram function with respect to MATLAB, this is actually the function that how it's used in MATLAB itself. So you call the spectrogram command here. X will be your input data or your input signal that has been discretized. This will be the window type and size. So this will be like a Blackman window, and then you want like 512 samples being the NW fits. The overlap size will mean basically how much overlap you want to occur. So in this case, we went NW divided by 2. The size of the FFT most of the time tries to coincide with the window size. So you'll say the FFT is performing on 512 samples. And then you finally need to actually indicate what the sampling frequency is in order to perform the spectrogram. So in recapping, basically, in using the STFT, this is actually for non-stationary signals. So like for music, audio signals, or real-time signals in particular, where you can't perform the FFT in one shot on the entire signal. So you actually have to keep on approximating the FFT as the signal keeps coming in or processing in order to get an accurate representation at the end of the FFT. So this is why the STFT is very important for real-time applications.